in Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello everyone, I'm Monica Dias, chemistry teacher at St. Xavier's Higher Secondary School, MAPSA. A very warm welcome to this chemistry class in this series of Prudent Scholars. Nature never ceases to amaze us with its beautiful and intricate patterns. The world of chemistry too is quite intriguing. I want you to have a look at this particular picture which shows crystals of a particular substance under a microscope. I want you to identify the substance. Well, if your answer is salt, then yes, you are right. These are crystals of NaCl, that is sodium chloride, as seen under a microscope. Well, NaCl is a common household commodity, that is rock salt. So they are known to have cubic arrangement. Here are some more crystals, this time of fluorite, which also crystallize in a cubic arrangement. Beautiful, aren't they? Let's go ahead and study about the various types of solids which include these, that is crystalline solids, along with their atomic structure and their physical and chemical properties in our chapter that's titled The Solid State. If you observe the arrangement of constituent particles, that is atoms, ions or molecules in a crystalline and an amorphous solid, you will notice a vast difference. The constituent particles in a crystalline solid are all arranged in an orderly manner, while it is not so in an amorphous solid. The constituent particles here are arranged in a random manner. Hence, there is also a difference in their properties. So let's distinguish between both the types of solids. A crystalline solid has a definite geometrical shape, while amorphous solid has an irregular shape. When cut with a sharp-edged tool, a crystalline solid generates plane and smooth surfaces, while an amorphous solid is going to generate an irregular surface. A crystalline solid has a characteristic sharp melting point, while amorphous solids soften over a range of temperature. Crystalline solids are called true solids, while amorphous solids are called pseudo-solids or supercooled liquids. This is because amorphous solids are known to flow like liquids, though it is at a very slow pace. Crystalline solids show long range order, which means there is a regular and periodically repeating arrangement of particles which are seen in the crystal, and this particular pattern repeats itself over long distances, and hence it is called long range order, while in amorphous solids, even if there is a pattern which repeats itself, it is over a short distance only, hence it is called short range order. These are a few examples of amorphous solids: rubber, gels, plastic, glass and candle wax. Glass, especially those that window panes are made of, do not break along regular planes, and hence it indicates to us that the molecular structure of glass is amorphous. Here are some examples of crystalline solids: fossil shell with calcite crystals and quartz, which is a mineral. Also, snowflake crystals are crystalline in nature. Let's now come to the classification of crystalline solids. These are broadly categorized into 4 main types depending upon the type of constituent particles present and the type of attractive forces between them. Molecular solids are further subdivided into non-polar, polar and hydrogen bonded solids. Let's see the type of forces present between them. Non-polar solids comprise of dispersion or London forces present between the constituent particles. Polar molecules show dipole-dipole interactions, and as the name suggests, hydrogen bonded molecules show the presence of hydrogen bonds between the constituent particles. All molecular solids are made up of molecules. Ionic solids comprise of ions which are held together by electrostatic forces of attraction. Covalent or network solids are comprised of atoms which are covalently bonded. And lastly, metallic solids comprise of positive ions which are dispersed in a sea of delocalized electrons, and the bonds which hold these constituent particles together are metallic bonds. Let us now come to inorganic crystal structures. The main feature of the structure of a crystalline solid is a regular and repeating pattern of constituent particles. The smallest building block of a crystal or the basic unit is called a unit cell. When a particular unit cell repeats itself along different directions, it generates a lattice structure which is also called a crystal lattice. Hence, if you look at the animation, you will realize how a unit cell, which is a basic building block, repeats itself along different directions to generate a 3D crystal lattice. A crystal lattice is thus a regular three-dimensional arrangement of points in space. I want you to observe this figure and infer the number of unit cells which are seen in this particular crystal lattice. Yes, your answer is 8. There are 4 unit cells above and there are 4 unit cells below. The portion that is highlighted in red is 1 unit cell. We now come to the parameters of a unit cell. A unit cell is characterized by 6 parameters, that is 3 edges A, B and C, and the angles between these edges, that is alpha, beta and gamma. Unit cells can be broadly divided into 2 categories, that is primitive or simple unit cell and centered unit cells. If you look at this figure, you will see that there is a unit cell with 8 atoms at its corners. This type of a cell is called a simple or a primitive unit cell. Centered unit cells are those which contain 1 or more constituent particles at certain positions in addition to those which are already present at the corners. They are of 3 types, that is body-centered cubic, face-centered cubic and end-centered cubic unit cell. Now let us look at this one. A body-centered unit cell has, as usual, 8 atoms at its corners along with 1 atom which is present at the body center of the cube. This is highlighted in green on the figure. A face-centered unit cell has 8 atoms which are present at its corners along with an atom which is present at the center of every face of the cube. These are the atoms which are being highlighted in the figure. End-centered unit cell comprises of 1 constituent particle which is present at the center of any 2 opposite faces besides the ones which are present at the corners of the cube. All crystals which are found in nature crystallize in any one of the 7 basic geometrical figures, and these are called crystal systems. Let's go ahead and see the 7 crystal systems in detail. As we have discussed earlier, these are all characterized by 6 parameters, that is 3 edges ABC and the angles alpha, beta and gamma. The 7 crystal systems are cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral and triclinic. Let's take an example of the cubic crystal system. We see here that the 3 edges A, B and C are all equal to each other and the angles alpha, beta and gamma are all equal to each other, that is equal to 90 degrees. Bravais, a French mathematician, showed that there are only 14 possible 3D lattices. If you check the first column in this table, we have the 7 crystal systems, and the next column gives you the possible variations. Take for example a cubic crystal system. It shows 3 variations, that is primitive, body centered and face centered. So also we have the rest, and if we count the total variations in column 3, they come to a total of 14. Hence we have 14 Bravais lattices. We now come to the calculation of number of atoms in a unit cell, and the symbol for this is Z. In the figure to the left, we have a primitive cubic unit cell. Look at the figure to the right. If you look at the atom which is highlighted in blue, I want you to think about this. With how many unit cells is this particular atom shared? The answer is 8. Yes, the atom which is highlighted in dark blue is shared with 8 other unit cells. So how much of this atom belongs to only this one unit cell? The answer is 1 by 8. Hence, keeping in mind that there are 8 corners to this cube, we will have the total number of atoms in one unit cell as 1 by 8 multiplied 8 times, and that comes to a value of 1. Hence, for a primitive cubic unit cell, the value of Z is 1. Let's calculate the value of Z for a body centered cubic unit cell. We have 8 atoms at the corners, and each of these atoms is being shared with 8 other unit cells. There are also 8 corners to this cube. So the first calculation remains the same as that for a simple unit cell, that is 1 by 8 multiplied 8 times, which comes to 1 atom. In addition to this, we also have an atom which is present entirely at the center of this unit cell, and it belongs only to this unit cell. It is not shared with any other neighboring unit cells. So taking this into account, we have a grand total of 2 atoms. Hence, for a body centered cubic unit cell, also abbreviated as BCC unit cell, the value of Z is 2. We now come to a face centered cubic unit cell. The first calculation remains the same. Now let's see what happens to the rest of the atoms. Observe the atoms which are highlighted in green. Each of them is present at the center of each of the faces of the unit cell. Look at the atom which is highlighted in black. With how many unit cells is this atom shared? The answer is 2, because it is also shared with the unit cell to its right. Now how much of this atom belongs only to one unit cell? The answer will be 1 by 2. Considering now that there are 6 faces to this cube, we will have the calculation as follows. 6 face centered atoms, and hence we have half multiplied 6 times. So which comes to, this comes to 3 atoms. Hence the value of Z for a face centered cubic unit cell or FCC unit cell is 4. We discussed the different Bravais lattices. Let us see some examples of the same. Emerald exists as a hexagonal crystal system. This is a picture of a rock containing 3 crystals of iron pyrite, and the crystal structure is primitive cubic. With an idea of the various crystal systems and Bravais lattices, let's now go ahead and solve a simple numerical regarding the same. 3 elements X, Y and Z crystallize in a cubic solid with X atoms at the corners, Y atoms at the cube centers and Z atoms at the centers of the faces of the cube. Deduce the formula of the compound. The given data tells you that X atoms are present at the corners, and hence the number of X atoms will be 1 by 8 multiplied by 8 corners of the unit cell. So we have accordingly we have a value of 1. As you are given that Y atom is present at the center of the cube, it is present as it is given that Y atom is present at the center of the cube, it belongs to that particular unit cell only and is not shared with any other neighboring unit cells. Hence, the number of Y atoms is 1. You are given that Z atoms are present at the face centers. So, as per the calculation discussed earlier, we know that the number of Z atoms belonging to a unit cell will be half multiplied by 6 faces, which comes to 3. Now, in order to generate the formula of the compound, we need to take a ratio of X is to Y is to Z. The ratio becomes 1 is to 1 is to 3, and hence the formula of the compound is XYZ3. Another similar example. 3 elements A, B and C crystallize in a cubic solid lattice with A atoms at the corners, Y atoms at the cube centers and Z atoms at the centers of the edges of the cube. Deduce the formula of the compound. Since A atoms are present at the corners as per the data given to you, the number of A atoms will be calculated in this manner: 1 by 8 into 8 corners, which makes it a value of 1. B atoms are present at the center of the cube as per the data given to you. Hence, the number of B atoms will be 1. As C atoms are present at the centers of the edges, the number of C atoms will be 1 by 4, because each atom which is present at the center of a particular edge will be shared with 4 other unit cells. So, we have 1 by 4 multiplied by 12 edges that a cube has, which makes it a value of 3. On taking the ratio of A is to B is to C, you will get 1 is to 1 is to 3, which makes your formula ABC3. I hope you have understood how to calculate the same, and please do practice further. We now come to the arrangement of constituent particles in a crystal lattice. Look at this picture carefully, which shows you stacking of oranges. I want you to compare these two pictures and tell me in which of these two arrangements is the empty space between the oranges minimum. If your answer is the one to the right, then yes, the answer is correct, because there is a lesser gap between the oranges in the pile which is shown towards your right. So, the arrangement looks something like this, where the available empty space between the oranges is minimum. We can extend this analogy to visualize the packing of atoms in a crystal by treating them as hard spheres, all of them being of equal size. Close packing is the arrangement of constituent particles in a lattice in such a manner that they occupy maximum available space in the lattice. Only then can we call this packing an efficient one. Let us come to close packing of spheres in one dimension. We assume that all atoms are spherical in shape and having the same size. If we pack them in one dimension, the arrangement will be in this manner. Remember, each of the spheres need to be touching each other so that the packing is efficient. Considering any one of these atoms, let us say for example the one which is highlighted in purple, we can now determine the coordination number, which is nothing but the number of atoms which are touching this particular atom. It is easy to understand from the figure that the coordination number of each atom in this type of arrangement is 2. Close packing in 2 dimensions. So, we now generate more layers. If we look at this type of packing, is it an efficient one? No. As we saw earlier in the example of the oranges, this type of packing is not efficient. If we compare this example to the one that we saw earlier, that is packing of oranges, this packing is not efficient because there is a lot of empty space which is present between the atoms. This type of packing is called AAA type of packing because each of these layers are stacked exactly above the other. What is the coordination number of each atom in this arrangement? You can easily see that the coordination number is 4. Now, if I join the centers of each of these spheres, we get a geometrical figure, that is a square. Hence, this type of packing is termed AAA type of packing or square close packing, and the coordination number is 4. This is what a 3D lattice formed by AAA arrangement looks like. We can observe here close packing of spheres in 2 dimensions. You will see that in this particular type of arrangement, which is called AAA type of arrangement, we have a lot of gaps or voids which are larger in size in comparison to this type of arrangement. Over here, you will notice that the second layer is placed in the gaps or the voids which are formed by the first layer. So, this type of packing is more efficient. If you take an arrangement of this type, that is AAA arrangement, and if you pick any one sphere, for example, the one which is shown here in orange, you will notice that the coordination number, that is the number of atoms touching this one particular atom, is 4. This type of packing is called square close packing arrangement. Let's come to another manner of arranging spheres in 2 dimensions. We have the first layer followed by the second one. If you notice, the second layer has the spheres which are placed in the gaps which are formed by the first layer. Hence, this type of packing is more efficient. This type of packing which is more efficient is called ABAB type of packing. Let's check the coordination number of a sphere in this type of arrangement. The coordination number is 5, and if I join the centers of each of these spheres, we get a hexagon. Hence, this type of packing is called ABAB type of packing or hexagonal close packing. This arrangement is also called ABAB type of arrangement because we have a layer of spheres, that is B, which is different from the initial layer, that is A. So, accordingly, this is termed as ABAB type of packing. Hexagonal close packing is also abbreviated as HCP arrangement. It makes more efficient use of available space in comparison to square close packing. Before we move on to 3-dimensional arrangement of atoms, let us see the meaning of the term voids, also called holes or interstitial sites. If there is a space surrounded by 4 spheres, that space or void is called a tetrahedral void. This is because if we join the centers of the spheres surrounding it, we get a tetrahedron. Similarly, if we have a vacant space which is surrounded by 6 spheres, we have an octahedral void. It gets its name because if we join the centers of these spheres, the geometrical figure obtained is an octahedron. We now see the 2 types of voids. We have here 3 spheres that is shown in green in the first layer and an orange sphere which is placed above. The void which is present in between is thus surrounded by 4 spheres. This type of a void is called a tetrahedral void. This is called an octahedral void. This is formed because we have 3 spheres below in one layer and 3 spheres above. So, the void will be surrounded by a total of 6 spheres, that is 6 atoms. The coordination number of a tetrahedral void is 4, while that of an octahedral void is 6. In many ionic structures, we notice that the anions which are larger in size form a close packed arrangement, while the cations which are smaller in size are going to occupy the interstitial spaces which are formed between these close packed anions. We now come to close packing in 3 dimensions. We generate the first layer, that is the spheres which are shown in green, that is labeled as A. We then generate a second layer, that is B. If you notice, the spheres of B are placed in the voids which are formed by the first layer A. Let's go ahead and identify the types of voids. So here they are. Can you name them? This particular void is an octahedral void, while the next one is a tetrahedral void. Since we are talking about 3 dimensions, we now also need to generate a third layer. We have the spheres A followed by the layer B. The octahedral and tetrahedral voids are seen in this particular figure. We now generate a third layer. If you observe carefully, the third layer is placed exactly above the first layer. Hence, it is labeled as A, and all these spheres are shown in black. We can move ahead and generate a fourth layer. This fourth layer is exactly above the spheres of B. Hence, if you continue this arrangement of spheres, we have an arrangement which is ABAB type of arrangement. This packing is called hexagonal close packing or ABAB packing, abbreviated as HCP. We now come to 3-dimensional arrangement of spheres. So we have the first type of packing, that is ABAB type of packing. We have the second layer, wherein this particular layer of spheres is placed in the voids which are formed by the first layer. The third layer will be placed in a manner such that this layer of spheres is exactly overlapping with the spheres of the first layer. This type of packing is called ABAB type of packing, also called HCP, that is hexagonal close packing. We come to another manner of packing spheres in 3 dimensions. So we begin with the first layer, which remains the same, that is a layer comprising of spheres of A. The voids of the first layer are covered by spheres of B. We have here octahedral void and tetrahedral voids. The third layer, that is C, can now be placed in such a manner that these do not cover any of the spheres, neither A nor B. So hence we generate a new layer, that is C. If we continue further, we can see the octahedral and tetrahedral voids, and producing more layers will be in this manner. The fourth layer will be exactly above the spheres A, and hence this will be an A layer followed by another layer B, and then again a layer C. The spheres in the first layer, that is A, followed by spheres of B, wherein the atoms are placed in the voids of a first layer, and now the new layer, that is C, will be placed such that they do not overlap with either A or B. So we can have an arrangement like this. This is called ABC type of packing or cubic close packing, abbreviated as CCP. Irrespective of the type of packing, that is whether it is ABAB packing or ABC type of packing, the coordination number of the central sphere, for example, in this figure, the one which is shown in white, is always going to be equal to 12. The number of voids which are generated depends upon the number of close packed spheres. The number of octahedral voids generated will be equal to n if you consider the close packed spheres. If you consider the number of close packed spheres as n, you will see that the number of octahedral voids generated will also be equal to n, and the number of tetrahedral voids generated will be equal to 2n. Let's solve a simple numerical based on this concept. A solid comprises of two elements P and Q. Atoms of Q are in CCP arrangement while atoms of P occupy all the tetrahedral sites. Deduce the formula of this compound. We begin with this. We consider the number of atoms of Q which are in CCP arrangement to be any variable. In this case, let us take it as x. By formula, we know that the number of tetrahedral voids generated will be twice x. It is given in the numerical that P atoms occupy all the tetrahedral sites. Hence, the number of P atoms will be equal to 2x. Taking the ratio of P is to Q, we get 2x is to x, that is 2 is to 1. And finally, the formula of the compound, it will be P2Q. Another simple example, you are given that atoms of element B form HCP lattice and those of element A occupy 2/3 of voids. Deduce the formula of the compound formed by A and B. Let's take the number of atoms of B in HCP lattice to be equal to x. So, by formula we know that the number of tetrahedral sites generated will be twice x. Since you are given that 2/3 of tetrahedral voids are occupied by atoms of element A, the number of atoms of A in the lattice will be 2/3 of 2x, which becomes equal to 4x by 3. We now take a ratio of A is to B. It works out to 4x by 3 is to x, and finally it becomes a ratio of 4 is to 3. Therefore, the formula of the compound is A4B3. This is a table which summarizes the packing efficiency in crystal structures. If you notice, among simple cubic BCC and CCP or FCC lattice, the most efficient packing efficiency is seen in case of CCP lattice, which is also called FCC arrangement. It comes to a value of 74%. The least packing efficiency is seen in a simple or primitive cubic lattice. The value of Z for all the three are given, that is, the Z values are 1 for a simple cube, it is 2 for a BCC lattice, and for CCP or FCC lattice it is 4. We can also calculate the value of R, that is the radius of the atom, by using the formulae as listed in the last column. A simple numerical based on this formula, D, which is also represented by the symbol rho, is the density of the element or solid. Remember that the density of the unit cell is the same as density of a given solid. Z over here is the number of atoms present in one unit cell. M is the atomic mass of the element. A cube is volume of the unit cell. As you know that for a cube, the formula for its volume is side cube. N represents Avogadro's number, that is 6.022 into 10 raised to positive 23 atoms per mole. A simple numerical based on this formula, calculate the atomic mass of an element that crystallizes in FCC lattice having density 5.209 grams per centimeter cube and edge length of the unit cell as 3 into 10 raised to negative 8 centimeters. You are given the value of Avogadro's number. This is the formula that we will use. It is very important, students, to list the data which is given to you and accordingly substitute it in the formula in order to avoid errors. So, the edge length given to you, that is A, is 3 into negative 8 centimeters. You are also given that the element crystallizes in FCC lattice, which means you are given the value of Z, that is 4. Density of the element is given to you in terms of grams per centimeter cube. It is very important to see that the units match. So over here you are given density in grams per centimeter cube and edge length is given in terms of centimeters. So there is no need to convert the units of edge length to anything else as it matches with the units of density, that is in terms of grams per centimeter cube. Avogadro's number, the value will be given to you. We now substitute this in the formula. So taking the unknown, that is m, on one side, on substitution the answer for molar mass comes to 21.17 grams per mole. It is very important to write the units at the end. Do not forget to write the units. Another example, iron having atomic mass 56 grams per mole crystallizes in a cubic lattice whose edge length is 286 picometers and has a density of 7.86 grams per centimeter cube. Identify the type of cubic unit cell. We use this formula, density is equal to Zm upon A cube Na. We list out all of the data. If you notice here students, the density of the element is given in terms of grams per centimeter cube and the edge length is given in terms of picometers. We cannot substitute the value of picometers as given because it needs to be in terms of centimeters. So we do the necessary conversion and the value is then 286 into 10 raised to negative 10 centimeters. On substitution, the answer comes to 1.977, which is taken to be approximately equal to 2. The reason for this is we are calculating the value of Z, and as you get your answer you need to know that Z can have only 3 values, that is either 1 or 2 or 4. Now in this case the value of Z is 2. So we then can identify the type of cubic unit cell. It is BCC, that is body centered cubic. We now come to imperfections in solids. Solids show two types of defects, that is point defects and line defects. By the name itself we understand that in a point defect, a defect is seen at a particular point only, while if the defect is along a series of points, that is along a line, then it is classified as a line defect. We shall now study point defects in detail, and these are classified into 3 types: stoichiometric, intrinsic or thermodynamic defects, which are subdivided into 4 various categories: vacancy and interstitial defect, which are shown by non-ionic solids; Frankel defect and Schottky defect, which are shown by ionic solids only. We also have impurity defects, where we have a cation being replaced by another cation with a higher charge. And lastly, we come to non-stoichiometric defects, under which we have metal excess defect and metal deficiency defect. So let us go through all of these in detail. Non-ionic solids show this particular type of defect, that is stoichiometric or intrinsic or thermodynamic defects. The first subtype under these is a vacancy defect. By looking at the figure, you would be able to understand that here the crystal is imperfect because there are 2 atoms that are missing, and hence there are 2 vacancies that are created in this particular crystal. In the next type of defect, that is interstitial defect, you will observe that there are atoms which are present at the interstitial sites. So we thus have 2 extra atoms which are occupying interstitial sites in this particular figure. Next, we have Frankel defect, which is also called dislocation defect. These type of defects are seen in ionic solids. Some examples of substances showing this type of defect are zinc sulfide, silver chloride, silver bromide and silver iodide. If you look at the crystal, it would have been a perfect crystal if all the cations and anions were present at their original sites. But if you notice, there is one cation which has moved out from its original position and it occupies an interstitial site. We have here a vacancy due to missing cation, and the cation occupies an interstitial site. What do you think is the effect of this particular defect on the density of the crystal? Yes, students, there is no overall impact on density of the crystal because the cation has only moved out of its original site and occupied an interstitial space in the crystal. So, density will remain the same. Coming to a Schottky defect, this defect again is shown by ionic substances only, and this is in those ionic compounds where the cation and anion have almost similar sizes. Some examples are sodium chloride, potassium chloride, cesium chloride and silver bromide. From the figure, you will notice that there are two cations which are missing and there are two anions missing from the crystal. The reason for the number of missing cations and anions being equal is very simple. The electrical neutrality of the crystal needs to be maintained. What is the impact on the overall density of the crystal? Yes, the overall density is going to decrease since these ions are missing from the crystal. We now come to impurity defects. Shown here in the figure is a crystal of sodium chloride where the ions of sodium are shown in red and the ions of chloride are shown in green. We also notice that two sodium ions are missing from the crystal. One of them is replaced by strontium impurity and the other one, that is the missing sodium ion, remains as a vacancy. Each sodium ion in the crystal has a charge of +1, and since there are two ions which are missing, the total charge missing from the crystal is +2. This missing charge, that is +2, is compensated for by having an impurity of the same charge, and this is why the impurity, that is strontium, has a charge of +2. We now come to non-stoichiometric defects. The first one is metal excess defect due to anionic vacancies. Shown here is a crystal of sodium chloride. This particular defect arises when sodium chloride crystals are heated in an atmosphere of sodium vapor. Thus, there will be an excess of sodium vapor outside the crystal, and this ionizes, giving sodium ions and electrons. The electron then moves into the crystal and replaces chloride ions. Now, once the chloride ions move out, they are going to combine with sodium ions and give you NaCl, that is sodium chloride, as a byproduct. Now, this particular electron which has entered the crystal gives the crystal a special property. It imparts color to the crystal, and hence these electrons which have now replaced chloride ions are given a name. They are called F centers or color centers. It is named F center because this word is derived from the German word Farbencenter, which means color center. In this particular example of sodium chloride, the electron is responsible for imparting yellow color to the crystal. We now come to metal excess defect due to the presence of extra cations at interstitial sites. A simple example of the same is zinc oxide, where you know that the ratio of zinc is to oxygen should be 1:1. On heating zinc oxide, oxygen is lost and zinc is in excess. Therefore, the formula changes, and instead of being ZnO, that is with zinc and oxygen being in the ratio of 1:1, it now becomes Zn 1 plus XO, indicating that the metal, in this example zinc, is in excess. The opposite is metal deficiency defect. A typical example of this is ferrous oxide, where the ratio of iron is to oxygen should be 1:1, but the composition is Fe 0.95O. The range is actually Fe 0.93O. to Fe 0.960, which indicates that there is a metal deficiency in the crystal. Solids can be classified into three main categories depending upon their electrical conductivity. We have insulators which show very low conductivity in the range of 10 raised to negative 20 to 10 raised to negative 10 ohm inverse meter inverse. The next in this category is semiconductors, which show conductivity in the range of 10 raised to negative 4 to 10 raised to 4 ohm inverse meter inverse, and lastly conductors, which have very high conductivity in the range of 10 raised to 4 to 10 raised to 7 ohm inverse meter inverse. These are examples of conductors and insulators. Substances like silicon and germanium are called intrinsic semiconductors. Their conductivity is too low to be of any practical use. Hence, we would like to increase their conductivity. This can be achieved by a process called doping. Doping is carried out by the addition of a suitable impurity to semiconductors. Doping can be done by adding an electron rich or an electron deficient impurity to a silicon or germanium crystal. Shown here in this figure, you can see silicon atoms. Now, each silicon atom has 4 valence electrons around it. These electrons are shared with the electrons of neighboring silicon atoms, and accordingly this sharing of electrons results in the formation of a covalent bond. This is a pure semiconductor. The electrons of each silicon atom are highlighted in red. Let us now understand what an N-type semiconductor is. A silicon atom or more is replaced by an element from group 15. In this example, we replace silicon with arsenic. Arsenic will have 5 electrons in its valence shell. Hence, you will notice that 1 electron is left free. This is called a mobile electron, and as we have more and more impurities which are added to the crystal, there is an increase in the number of mobile electrons, and as a result there is an increase in conductivity of the crystal. A p-type semiconductor will be one in which silicon atom is replaced by any atom from group 13. In this example, we have boron atom which has replaced silicon. As you know, boron has 3 electrons around it, and there is a vacancy which is created, which is called an electron vacancy. The neighboring electrons try to occupy this vacant position as seen in this animation. Hence, there is an increase in electrical conductivity of this crystal. Extrinsic semiconductors are divided into 2 types, as we have just seen, that is N-type and P-type semiconductors. N-type of semiconductors are obtained when crystals of a pure semiconductor are doped with electron-rich impurity from group 15, and these can be either nitrogen, phosphorus, arsenic, antimony or bismuth. A P-type semiconductor is obtained when silicon or germanium crystal is doped with electron deficient impurity, which can be any of the elements from group 13, that is boron, aluminium, gallium, indium or thallium. We now come to the last subtopic in this chapter, that is magnetic properties of solids. It is important for you to understand that the reason for magnetic properties in substances is the presence of electrons. Each electron in an atom behaves like a tiny magnet. It is also very important for you to understand the meaning of the word domains. A magnetic domain is a region within a magnetic material in which magnetization occurs in a uniform direction. This means that individual magnetic moments of the atoms are aligned with one another and they all point in the same direction. Solids are categorized into 5 different types based on their magnetic properties. The first one is paramagnetic, the next is diamagnetic, ferromagnetic, antiferromagnetic and ferrimagnetic. Paramagnetic substances are those which contain one or more unpaired electrons. These are weakly attracted by a magnetic field, and in the absence of a magnetic field, they lose their magnetism. Examples of paramagnetic substances are oxygen and copper in the +2 oxidation state, that is cupric ions. Diamagnetic substances are those in which all the electrons are paired. These substances are weakly repelled by a magnetic field, and examples of the same are water and sodium chloride. Ferromagnetic substances are very strongly attracted by magnetic field, and these substances can be permanently magnetized. Examples of the same are iron and cobalt. In an unmagnetized piece of a ferromagnetic substance, you will notice that the domains are randomly oriented and their magnetic moments get cancelled. But in the presence of a magnetic field, all their domains are arranged in this manner, that is in the direction of the magnetic field itself, and therefore a strong magnetic effect is produced. Antiferromagnetic substances are very strongly repelled by a magnetic field, and an example of the same is manganese oxide. If you notice the domains, you will see that the domains are oppositely oriented and they cancel out each other's magnetic moment. Lastly, ferrimagnetic substances. The magnetic moments in these are aligned in parallel and anti-parallel directions in unequal numbers. These are weakly attracted by magnetic field, and an example of the same is magnetite. With this, students, we come to the end of this chapter of solid state. I leave you with a quote by Ralph Waldo Emerson, which reads, "Nature never hurries. Atom by atom, little by little, she achieves her work." In a similar manner, students, whatever the effort that you may put in towards your studies and however little you feel the effort may be, always remember it is definitely going to help you achieve the greater goal, that is to achieve success in your studies. With this, I thank you and wish you all the very best in all your future endeavors.
Prudent Scholars, powered by Lupin Pharmaceuticals.